Okay, in this video we're going to talk about related rates. This goes with section 2.8 in our textbook. The first thing you need to know is if you have a relationship between two variables and those two variables are changing with respect to time, then their derivatives or their rates of change are also going to change with respect to time. And that's what we have right here. We've got a relationship right here, y is equal to 2x, okay? And I'm going to change that. So our variables are related, y is equal to 2x, this is our relationship, and if they're changing with respect to time, then the derivative of each side of that equation is also going to have to be related, their rates of change, with respect to time down here. Okay, let's go over and take a look at the first example. Okay, we've got the variables of x and y, they're differentiable functions of t, and they're related by the equation, which is given to us right here, y is equal to x to the third plus 2. And we know that when x is equal to 1, the derivative of x with respect to t is 3. We would like to find the derivative of y with respect to t when x is equal to 1. Okay, so what we're going to do is we're going to take the derivative of both sides of this equation with respect to t. So we have d dt of y is equal to d dt of x to the third plus 2. Okay, now the derivative of y with respect to t, that's just dy dt. There should be a dt there. Alright, and then on the other side, the derivative of x with respect to t, this is going to be 3x squared, and then using the chain rule, we'll have over here also a dx dt, and then of course the derivative of 2, that's just going to be a 0 back here. Okay, so now that we have this equation, we just need to fill in the parts. We know that x is equal to 1, so I'm going to put that in here. We're going to have dy dt is going to be equal to 3 times 1 squared, and really the dx dt, we know that also it was given to us. And it's right here, it's going to be equal to 3. So we're going to be multiplying this by 3, and of course we can add that 0 back here, but we really don't need to. And then we put all that into the calculator. 3 times 1 squared times 3 plus 1, that's just going to be 9. That means that the derivative of y with respect to t is going to be 9 when x is equal to 1. This is what we were looking for. Okay, let's take a look at example 2. A pebble is dropped into a pool, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a rate of 2 feet per second. At what rate is the total area of disturbed water changing when the radius is 3 feet? Now, in case you didn't know, when you throw a pebble into the water, it automatically makes a circle, but then that circle kind of spreads out and gives you a second one, and then it gives you another one, and it gives you another one, and so on, until eventually the ripples have just spread out so far. Okay, so what we would like to do is we'd like to take this and we'd like to make it look like our previous problem in example 1, where we have a rate of change, and we also have an x, and then we're going to try and find the derivative and figure out what the derivative of the area, or dA, over dt is, the derivative of the area with respect to the time. Okay, so let's start with things that we know. Alright, one thing that we know is that the radius is going to be equal to 3, or 3 feet. That's told to me right here. Another thing that they gave me is a rate at 2 feet per second. This is a rate of change, and what that means is that the derivative of the radius with respect to time is going to be 2 feet. So the change in the radius is 2 feet per second. Okay? Alright, now what we're missing in this that we had in the other one is an equation. Okay, well remember, we're dealing with circles, and we know the formula to find the area of a circle is pi times r squared. So there's our formula right there that we're going to be using. Right? And let's do exactly what we did on the previous problem. We're going to find the derivative with respect to time of both sides of this equation. Like so. Alright, so the derivative of a with respect to time, this is just going to be dA dt. Now remember, this is what we're trying to solve for. That's what's asked for in the problem. Over here, pi is just a constant. So we're going to have pi times, now the derivative of r squared is going to be 2r, and then we're going to have dr dt, the derivative of the radius with respect to the time there. Okay? Okay, and now we should be able to fill in the parts that we knew, which were these two things over here. So I can put my 3 in for the r, and I can put my 2 in for the dr dt, and we can solve this problem. So dA dt is going to be pi times 2 times 3, the radius, times 2 dr dt, and this is going to give me, let's see, 2 times 3 is 6 times 2 is 12. This is 12 pi, and we are looking at feet per second. Alright, so what rate is the total area changing when the radius is 3 feet? It's changing at 12 pi feet squared per second. And I changed it to squared because we're doing an area here, and our unit should be squared. Here are the guidelines for solving the problem, which is kind of what we just did, going through all the steps. You need to identify your given information and what it is you need to know. And if you can make a sketch, you should. Okay. Then you want to write an equation if it's not given to you for the variables whose rates of change are trying to be determined. All right. Use your chain rule so that you can take the derivative of both sides of the equation, and then do your substitutions in step 4 here. Just remember that you need to differentiate first and substitute later. Don't substitute first. So don't change these two steps in the wrong order. This particular chart is given to you in your textbook. It is on page 153, but I just went ahead and copied it over here in case you need some of the models for some of your common rates of change. Here they are. Okay, and then we can move on here to example 3. We're back to the profit problems, which we've done earlier. A company's profit P in dollars from selling X units of a product can be modeled by the formula P is equal to 200X minus 1/2 X squared. The sales are increasing at a rate of 10 units per day. Find the rate of change of the profit in dollars with respect to time in days when 50 units have been sold. Okay, so things that we know. We've got our rate right here. Alright, so that means that this is going to be 10, and we want X to be 50, and we have our equation up here. And this should be dx dt. Alright. Let's take the derivative with respect to time of both sides of our profit equation up there. We have 200x minus 1/2 x squared. Alright, so the derivative of the profit with respect to time, this is just going to be dp dt. Over here, the derivative of 200x is just 200, and then we'll have a dx dt. And then the derivative of negative 1/2 squared is going to be, let's see, 2 times negative 1/2, this is negative 1. And then that'll be to the first power. And then this one is also going to have the dx dt on it because we took the derivative of x with respect to time. So we're using the chain rule because there are no t's here in the parentheses, so we're showing that we took the derivative of x with respect to t. Okay, now I think we can plug in our information because we've got our dx dt, we know what that is. We have an x right here, so we can find the derivative of the profit with respect to time here. We'll have 200 times 10 minus 50 times 10. Now the 200's right here. The dx dt we said was equal to 10. X we said was equal to 50. And then another dx dt we know is equal to 10. And we can put all this into our handy dandy calculator, and I believe this is going to give me $1,500. And then this is going to be per day, because our units right here tells me that our time is in days. And here's our last example, example 4. A company is increasing the production of a product at the rate of 200 units per week. The weekly demand function is modeled by P is equal to 150 minus 0.002x, where P is the price per unit in dollars and X is the number of units produced in a week. We want to find the rate of change of the revenue in dollars with respect to time. Okay, did you catch that? We're given the P equation here, but we're asked to find the derivative with respect to the revenue. So keep that in mind because we're going to have to do something with that in just a minute. Alright, so we're finding the derivative with respect to time when the weekly production is 2,000 units, and then we want to know if that rate of change is greater than 20,000 per week. Okay, so we need to back up to an earlier section in chapter 2, and that was that our revenue function is actually equal to x times whatever our demand function is. So we need to know what our revenue function is, and that's probably the first thing we should do. Alright, so the revenue function is going to be x times, and then our demand function is 150 minus 0.002x, which means that our revenue function is 150x minus 0.002x squared. Okay, things that we know. Let's see, the weekly production we want to be 2,000 units, so we want x to be equal to 2,000. And let's see, our rate up here is given to us to be 200 units per week. So that means that our dx dt is going to be 200. Okay, let's see if we can find the change in the revenue with respect to time. We will find the derivative of r over here with respect to time, and then we will find the derivative of 150x minus 0.002x squared. Alright, over here on the left, the derivative of the revenue with respect to time, that's just going to be dr dt. Over here, the derivative of 150x, that's going to be 150. And then with respect to time, we're going to need to have a dx dt on it. And then the derivative of 0.002x squared is going to be 0.004x. And then we're going to need to have a dx dt over here as well. And again, this is just an application of the chain rule. And now I think we can plug in our information because we know dx dt, that's right here, and we know x, that's right here. So I'm going to come up here where I got a little bit more room, and dr dt is going to be equal to 150 times 200, this is my dx dt, minus 0.004 times 2000, that's my x, times 200, that's my dx dt, and then we should be able to put all that into the calculator. And that is going to give me $28,400 per week. And so when we answer our question here, is the rate of change greater than 20,000 per week, we can say yes, the rate of change is more than 20,000 per week. And that's it.